All right, so afternoon. So we're still on level 1 packaging, and we talked a little bit about area array packages. So we'll do a whole session, short one, a whole session on just some different incarnations of area array packaging. There's quite a diversity of area array packages. And then I'll end up with some multidimensional, just 1 or 2 slides on, we talked about it yesterday. I'll go back to 2.5 and 3D stacked packaging. Okay. All right. So, and along the way, thanks to Anandaroop, we'll have a few samples that we'll zoom in from there and share, and then maybe we can pass them around. Is that okay? All right. All right. Okay. So once again, just to highlight, we are still on first level. We're going to talk about this part of the process, but the packaging is all going to be area array now. Okay. Much like some of the area arrays you saw in the morning. So let's start out with some of the forms we've talked about already. So pin grid arrays. This is a ceramic pin grid array. The underside, the chip would be on the what's on the bottom of this picture. Ball grid array. You can see both sides. This is the plastic ball grid array. It has an organic laminate as a substrate. Okay, and die has been mounted on that organic substrate and then molded over. And on the back side of it, the underside of this is what you're seeing here, are the solder balls. Okay. And maybe I can use this to, can we switch over to overhead? Yeah, okay. Okay. And can we zoom down on it? Okay, great. So this is a sample where it looks like there's a large underfill flip chip die. So the top die is, actually it's not a, looks like a glass. Is that a die? Really?
That's a test vehicle.
Okay.
Thermal test vehicle.
Okay. Okay, thermal test vehicle. Okay. So there's underfill under it. So this piece that mimics a chip has been underfilled. So typically that could be a flip chip underfilled die. And then you've got the organic substrate. And if I turn this on its edge, and maybe you can see it. Let's see if the lighting is best over here. You can see the solder balls. So there's solder balls on the underneath. And it's a pretty high I/O count. You can see there's it's split in 4 quadrants. It's a full area array. And fairly high I/O count. Do you know how many there are? Let's see if I can, no, it's in letters, so it's, okay, it's 42 by 42. Someone do the math, 800 and whatever, okay? So this is 1 mm pitch, yeah, yeah, yeah. So, sorry? Yeah, exactly, it's 42 by 42. So it's, yeah, yeah, 42 by 42. Okay, so that's BGA. Now this one is most likely, I cannot guarantee it, but this one is most likely a face up die inside wire bonded, not a flip chip. We'll see both versions soon. And this is only 225 I/O, quite a bit smaller than the one you just saw. Can we pass that around? Is that okay? Yeah.
Level doesn't have an underfill because it's between laminate, it's between.
Right. So that's a very good point. So I missed mentioning that. So because it's an organic substrate for the component, and then it's soldered onto another organic PWB, there's not much CTE mismatch there. So of course, in the center region, there will be a little bit because the die will be reinforced in the center region of the component laminate, component substrate. So that'll constrict the CTE. But effective CT, but it's not big enough problem that they had to put underfill for the second level. The underfill is only in the first level. BGAs are now used quite extensively without underfill. Flip chips are not, but BGAs are used quite extensively without underfill. If it's an organic laminate like that component or like this component. And this one is a land grid array. So this is a famous AMD chip. I just got the image out of the web. And this is just a pad over there. There's nothing else. There's no pin. There's no solder. So that's just a land grid array in this format. Okay. So again, it's an organic substrate, and under the lid, of course, is the chip. Okay. Okay. So this is that same ball grid array image carried over here, and then here's the details of the package itself. So you can see the routing over there, and then the area array balls over here. So this one is a little bit different. You'll notice that this one is a little bit different from this one. This one has a uniform area over here. This one has two sets of arrays with some gap in between. There are no solder joints in this region, and solder joints in the inner region here and in the outer region here. So two partial arrays as opposed to one full array. Okay.
If you take the other package and show the underneath, even though that's a pin grid, no, not that. If you take it up.
All right. Yes.
So here you can see.
Yes. So let's put that on. This is so this is a. Okay. Let's zoom in. Yeah. So this is a pin grid array. If I hold it to the side, you can see the pins. Okay. There's a pin grid array with a whole bunch of components in the middle. There are some. So there's some dual inline packages, and then some passives also. Everything.
Everything is landside caps.
Oh, right. Okay. All right. Yep. So just passives here. And you can see that this is a partial array. So nothing in the middle, of course, that's where the components are. But it's a partial array, a little bit like the outer array of what's on the screen, going to come on the screen now. Yeah, a little bit like the outer array of that. Okay. Yep. Okay. Okay, so and inside these BGA packages, of course, it can be multi-chip or single chip. Okay, so they could be, or it could be a system in package. They could be not just active. There could be passives. You saw passives on that board. And the reason, of course, for this area array packaging is that you are utilizing a lot more space now for I/O. If you only use the perimeter, you wouldn't be able to fit in this many I/O. So much more dense packaging of I/O, so that's the space efficiency here. And for surface mount, these BGAs work very well because of the self-centering, and we'll talk about that in a later slide. If the package is a little bit misaligned when you mount it, they will center themselves when it's undergoing this, when the solder is solidifying. And again, we already talked about, just like flip chip, you've got very short electrical joints, so better electrical and thermal performance, and you don't have the lead height to deal with, so lower profile, so it can fit in tight spaces, and don't need special tooling. Just existing pick and place and handling will do the job. Okay, so this is the slide that talks a little bit about the self-centering. So for example, if the component was misaligned when you set it down, then basically when you melt it during the reflow process, the surface tension forces are going to pull that back, and it'll self-center, so it'll get realigned as it solders. It'll realign because of self-centering forces. So that's one of the advantages of either flip chip or BGA. They will, to some extent, self-align, so the pick and place is much more forgiving. All right, so this is where we see the miscellaneous incarnations of what the arrays can look like. They can be aligned. The joints could be aligned, or they could be staggered, so there are various combinations. Some are full grid. Some are full grid with the corners removed, okay? And the corner joints are often the most stressed ones because it has the highest distance from the DNP. So sometimes removing it also helps from a reliability perspective. You don't use that joint, so the highest DNP joint cannot fail because there is no joint there. Okay, or sometimes people put in those joints but make them dummy mechanical joints. They're not electrically connected. They're just there for mechanical strengthening, but they're not electrically connected because those are the ones most likely to fail. Now you have to be a little bit careful. depending on the component design, sometimes it's the corner joint that's most likely to fail. Sometimes it's the one under the furthest corner of the die shadow that is most likely to fail. So for example, if in this component the die is sitting over here, it is possible, depending on the CTE and the compliance of the substrate, and depending on how big the die is, it's possible that this one may be at a higher risk of failure than that one. And I'm going to ask the students here to suggest why. So this joint is at a much higher, longer distance from the center than that joint. But if the die only extends up till here, there is a possibility, depending on the geometry and the architecture, there is a possibility that this one may be at a higher risk of failure than that one. And let me define the architecture a little bit. We're talking about an organic laminate, much like the one you're carrying around. Okay? So it's a die mounted on an organic substrate. And let us say it's a face-up die with wire bond on the backside of this component. And sorry, it's actually a flip chip because it's an area array here too. So it's a flip chip and underfilled. And the point is there a possibility? Can you foresee any scenario by which this joint may be at a higher risk of failure than that joint?
Yes.
Let's throw the question to the students. I know you know the answer. So what is causing the failure? Why would the solder joints fail? Different expansions. Different expansions between what and what. So I'll draw that package over here. Let's say I've got so this is an organic substrate. Okay, by organic I mean it's pretty much close to the same material, and this is the BGA. It's close to the same material as the printed wiring board, organic PWB. And over here, let us say I have the flip chip joints. Okay? And the statement I'm making is this joint may be at a higher risk of failure under the die corner over here. This joint may be at a higher risk of failure than that joint, although that joint is at a longer distance from the center than this joint is. Why do you think that might happen? So this is silicon, this is organic laminate, this is organic laminate, and these are the solder joints. Okay? Why do you think that might happen?
Different CTE between the die.
Say it again.
The different CTE between the
Right.
silicon.
Right. And what is that doing? What is that? So normally you'd worry about difference between them affecting these solder joints, right? What?
The angle of deflection will be more towards, I mean, due to the difference in CTs, there will be more deflection here.
Okay. So I think you're onto the right answer. I'm going to rephrase that a little bit. Think about this part of this component. So this whole thing is your component, okay? Think about this part of the component versus this part of the, so this part of the component versus this part of the component. So if I look at an effective CTE of this part, alpha effective, and I'm going to call that part 1, region 1, this portion I'm going to call region 2, and if I look at the effective CTE of region 2, which one do you think is likely to be higher? Higher? 2 will be higher because the silicon reduces the effective CTE, right? So this CTE over here is, let us say, C1, 2, 3. In fact, if there's no mold compound there, then alpha 3 and alpha 2 are about the same. So the point is, the bigger delta alpha is really ends over here. After that, there's not much of a difference in the alphas. I mean, overall, there's still a difference because this portion, region 1, has pulled back region 2 as a whole. But even then, the shear strain over here may still be smaller than shear strain over here. And that's quite common. In large dies, we see that quite often. If we go back here. So if you have a fairly large die, we see quite often that the one that's at the outer corner of the die shadow or the die footprint may fail before the one at the far outer corner of the package. Okay. So bottom line, you have to be a little bit careful with these designs. A little bit of analysis is needed in order to see which are the highest risk joints over there. So just as
I want to add up some
yeah,
input to here.
yeah,
The failure rates, if you compare to the corner
Mhm.
ones and the inner corner.
Mhm.
So if you see the corner ones, it will be only in the corners. It's like a triangle. The
Right.
failure will be in the four corners. But you take in the inside, the square, it will be the whole, the row and the column.
right, right. So there it gets, and that's because of the underfill. The effect, the diagonal, the length effect gets muted a little bit. So all around the edges, it'll fail. Yeah, good point.
We like that center square can't be like tilted by 90 or something to cancel out the.
No, that's still going to have the same
No,
problem.
Not 90 and 45 degree, like a rhombus type thing.
Okay.
No, what
That's still going to have the same distance from, so even if I turn that over, I have the same distance to the center. Right.
See, whatever the pin grid or the ball grid, whatever you placement you do it is like a tilted by 45 degree. So we have, right now, all the things like if you see outside the world, these are world ones. If you see the outside world, it is a balls anywhere concept. It can be in a 45 degree.
It can
It
be.
won't-
Yeah,
It is
yeah.
not that there.
Yeah.
So here, what are the stresses? They, sir, as sir told, is like the die shadow. So wherever the shadow of the die, that pins will be get affected.
Mhm.
Whether whatever you tilt it.
Right. So there, if you want to have some non-functional joints, like we talked about putting non-functional joints here because of the reliability risk, you would have to decide whether you want to make that the non-functional joint or these the non-functional joints, because those are the ones that might be at higher risk. Okay. Let's see what else. There's another aspect to this. When we say the corner joint is at risk, it's not that simple. Unfortunately, especially when it comes to lead-free solders, there's a lot of piece-to-piece variability in microstructure, grain structure of the joint. So even if the stress is identical, two different joints with two different grain structures are going to have two different times to failure. They're not going to fail at the same time. So it's quite possible, and we have seen this in our testing, it's quite possible that the corner joint, although it's seeing the highest stresses, may not be the one to fail. The one next to it may fail. It still has pretty high stresses, and it may have a worse case microstructure than the corner one. It's loaded in a bad direction of the tin grain, whereas this one is, the loading happens to be in a strong direction of the tin grain, and that one may survive. The corner one may survive longer than the one next to it. So we've seen that before. So it's really the few joints in the corner that are at risk, because you don't know what the microstructure is for each one of them. So it's a little hard to predict exactly which one. You know it'll be something close to the corner, but exactly which one is sometimes hard to predict. In tin lead solder, it was always the corner one, because there wasn't that much microstructural variability piece to joint. But that's no longer the case in SAC. Okay. And I'm sorry. And then the partial arrays is, again, the terminology is central with central connection, with no central connection. Okay. All right. And of course, by now, a lot of these terms should be familiar to you. Ball grid arrays can be on ceramic packages. This one is not familiar. That's a new terminology, and I can't remember if I have a picture of it, so I'm going to draw it. So think about the strain. In fact, I'm going to use this slide. This sheet of paper. So think about this expression we wrote for strain here. It had the height of the solder joint on the denominator, which means what? If you make a taller solder joint, the strains and stresses are less, the shear strains are less, and therefore it should last a little bit longer. Because as the strain gets higher, the fatigue life gets smaller and smaller. Okay? So if I make the solder joint taller, I can make the shear strain go down, therefore fatigue life, that's NF stands for cycles to failure, fatigue life will go up. We'll talk much more about fatigue life in day 5, unfortunately not yet. But I just want to explain where that ceramic the column grid array is coming from. So think about the ball grid array now. What we would like to do is make these joints taller, right? The problem is it's a sphere. How do you make a sphere taller? All right. Well, What if we get away from a sphere? Make a column. So make the column taller and taller and taller. So ultimately, it looks like this. You have a component that's standing on tall pillars of solder. So these are solder. Solder columns. Okay, and this is the PWB. This is the BGA component, not BGA, column grid array, CGA component. So it's a column grid array component. Okay, so that's also used in some specialty applications. So that's what you're seeing over here, ceramic column grid array packages. This one, WBPBGA, is a plastic ball grid array, but inside the chip is face up wire bonded. Okay, and I'll show you some pictures of that later on. And this one is a plastic ball grid array, but inside is a flip chip BGA, a little bit of a similar architecture to what's being passed around. And this one is a TBGA. This one is the die is tape automated bonded, tab bonded onto the substrate, and then the substrate is BGA bonded onto PWBs. Okay? So depending on the architecture, again, you have all these permutations and combinations. Okay, so look at a ceramic ball grid array as an example. So what would you say this is? So this is a ceramic base. Here is the solder ball, and those little pieces over there are just a cartoon schematic of the way these balls are attached. So the solder ball is attached to the base with tin lead solder, okay? And the solder ball itself is made of 9010 lead tin, so that's a high melt temperature ball. And it's attached with tin lead eutectic solder to the base, and then soldered onto the PWB with tin lead eutectic solder paste. The component itself has a die that is flip chipped down, so it would be, it's not on this list, it would be an FC CBGA, flip chip ceramic ball grid array. Okay, so that's what this one is. It's an FC CBGA. Okay, so you would basically get the, and you can look at a cross section there. So that upper eutectic portion is over here. The component is in the top side. This lower eutectic portion, eutectic solder, is over here. And in between, you can see the dark region is the high lead, high melt temperature solder ball. So you take these solder balls, you attach them first to the ceramic component, and that's how you sell that component. And then what you would do is you would take that component, flip it over, and put down tin lead solder paste on the board, or lead-free paste, whatever you're using. And then you would place the component on that solder paste, and then you would reflow it and join them. So fatigue failures, when they happen here, usually happen in the eutectic portion, not in the high lead portion. Okay. All right, so let's talk about this one. Now life is going to get a little bit more complicated. We're not only going to talk about in-plane mismatch, now there are additional stresses being generated because the package also warps. Okay, why is the board warping? Well, that's because you have a component on one side. The component has a certain stiffness and CTE. There's nothing to balance it on the other side of the board. So if the board is not very stiff, it has some flexibility, then as you heat it up or cool it, this portion is expanding a different amount than this portion. So now the neutral axis of the board has moved off the center, and now the board will start to bend depending on whether the component is shrinking or expanding relative to the PWB. So not all the mismatch goes into a shear deformation. Some of it goes into warpage. Okay. All right. Let's see. So you have to be a little bit careful. That when I said neutral axis, I did not mean that. That is the neutral, vertical neutral point. I meant the bending neutral axis, which is horizontal. Okay. All right. Okay. So so that is the effect of the global CT. So you have some amount of shear deformation and some amount of warpage of the whole assembly that's what is caused by the global CTE mismatch. And global CTE mismatch refers to the mismatch between the component and the PWB. In addition, there's a local CTE mismatch, and I talked about that when I talked about Kovar leads, and I talked about how there's a CTE mismatch between the lead and the solder itself. It's a similar situation here. The module, or the bond pad on the module, has a certain CTE, and the solder has a different CTE. So if the module is expanding a larger amount than the solder, then you're going to have a mismatch at that interface. Same thing on this side. If the PWB is expanding a different amount, PWB and the bond pad are expanding a different amount than the solder, then again you have a mismatch of expansion at that interface. So that is a local CTE mismatch. So the net effect is a sum of the global CTE mismatch and the local CTE mismatch. And we have to consider all of that when you do solder fatigue analysis in some detail. You consider the effect of all of those. Okay. And this is particularly bad in ceramic ball grid arrays rather than PBGAs. In ceramics, the substrate has, the component has very low CTE. The solder has a much higher CTE, so you get a pretty large CTE mismatch over there. Okay. Same thing if you're going to put them down on ceramic substrates, like the C4. If you put it down on ceramic substrates, again, you have a big CTE mismatch between the solder and the substrate on this side. And failures, when they happen, I mentioned that the failures happen typically in the eutectic region, and you can see that. The dark is the high lead solder ball, and you can see that the fatigue failures have all occurred in the eutectic regions. Okay. All right. So let's look a little more closely at one of these. So what's going on in that joint? So how do we add up the global and the local CTE mismatches? So let's take that corner joint and look at what's happening. So when I heat it, typically the PWB, most general PWBs have a higher CTE than the components, because the component has the die in it, so that restricts its CTE. So if the PWB expands more than the component, then this is the shear deformation in the corner solder joint. Fair enough? Yes? Okay. So think about these four corners now. Okay. Think about these four corners that are seeing those shear strains. And the reason I want to focus on those corners is that's where the strains will be highest from the local CTE mismatch, which I have to add on. So now think about the local CTE mismatch. Let's say it's a ceramic module, in which case the solder is going to expand a lot more than the pad over there. So when you heat it, the solder expands more, pad expands less. So you can see that's the deformation due to the local CTE mismatch. So if I start out with an initial approximation of just cylindrical joint, then that becomes barrel shaped because the solder is expanding more than the pad can. Everyone agree? Okay. So now look at the sign of shear in each of these four corners. This shear direction is opposite to that shear direction. Do you agree? This shear direction in quadrant 2, this shear direction is the same as in this shear direction. So the local CTE mismatch and the global CTE mismatch will cancel each other to some extent in quadrant 1, but reinforce each other and aggravate each other in quadrant 2, and the reverse, diagonally reverse in quadrants 3 and 4. So quadrants 2 and 3 are seeing the worst case summation or superposition of global and local CTE mismatch. Quadrants 1 and 4 are benefiting from cancellation of global and local CTE mismatch. Okay? So failures typically will start in those two corners and then propagate. Now you might say, hey, I see a big failure in quadrant 4 also. Well, that probably started in quadrant 3 and then propagated out all the way. Okay? And where it hasn't propagated all the way, you can see it is in quadrant 2. Okay? All right. So those two, quadrants 2 and 3, it's an additive situation. The two are adding. And quadrants 1 and 4, these two are subtracting from, they're canceling each other. So I'm calling it subtractive. Okay. So if you were to do a more detailed, like a finite element analysis or something, you'd be able to see all of this directly. You would see your highest stress concentrations or strain concentrations would be in these two diagonal corners, and quadrants 1 and 4 would have much less strain than quadrants 2 and 3.
So this is whatever you are explaining is about a particular ball.
One particular joint, yes, yes, yes. So I'm now zooming in on the joint that's at risk, the one in the corner, and trying to understand what exactly is that joint experiencing, right? Looking at it in more detail now. Okay.
There's the bit I'm confused that I got the diagonal corners.
Okay, yeah.
Then I realized.
Yes, I'm talking about the diagonals of the joint as opposed to diagonal of the component. You're right. You're right. I should have clarified that. Okay. Okay. Here's the column grid array. So that's the picture I was trying to draw for you. Here's the slide for it. So now these, instead of solder balls, solder columns have been soldered onto with eutectic solder onto the component, and then you would solder it again on the PWB side when assembling the board. And you can see cross sections of some column grid arrays. That's the joint on the component side. This is the joint on the PWB side. Okay. And you can see how much those deform. This is ATC stands for accelerated temperature cycling test. So these assemblies have been temperature cycled, heated, cooled, hundreds of cycles. And you can see as a result of the CTE mismatches, there's been cumulative deformation in these column grid arrays. They have now permanently changed shape and no longer look straight. Okay. All right. And again, this is FCCCGA. That means the die is flip chipped onto the ceramic base, and then it's a column grid array. So that would be an FCCCGA. Okay. Here's a wire bonded version, not flip chipped, but wire bonded version. So this is face up, wire bonded, over molded. So you can see the over mold over here. Bottom side, you can see that it's a partial array. Okay, and of course the pads have been redistributed internally. So some of these, and by the way, some of these sometimes are not functional joints, functional pads. Sometimes they're thermal pads. So there may not be any electrical signal in them. They are there to remove heat from the die. Okay.
Is it a pin or is it a passive?
I'm sorry. Say it again.
It looks like it's a passive.
Yeah. Slightly bigger.
Oh, maybe. That's possible. That's possible. Let's zoom. Oh, I gotta get out of. Yeah.
Not a pin.
Yeah, you're right. These might be. In this case, these might be passives.
Yes.
Yeah. So here, these are passive components. But having said that, sometimes we put in thermal vias over here, thermal pads over here, and that connects to a metal pad over there, and the purpose of that would be to remove heat from the die. In this particular case, though, it's more like the passives that you saw in the PGA. Okay. So the substrate is a laminate, in this case, organic laminate, made in this case out of BT resin, which is slightly higher temperature organic laminate than standard FR4 laminates. FR4 is the most classical resin that's used for printed circuit boards. Normal FR4 has glass transition temperature of about 125 degrees C. High temperature multifunctional FR4 would be a little bit higher than that, about 150 degrees C. BT is probably just a little bit higher than that. And then these have eutectic solder balls underneath. Okay. So that would be a very classical standard wire bond PBGA. OMPAC is a name given to a particular Motorola architecture, one of the early PBGAs that were designed by Motorola and had this acronym OMPAC. So that's where that term comes from. Okay. Here's a cavity down, which means the die is below the substrate, as opposed to here the die is above the substrate up. Okay, that's what that cavity up means. And here the die is underneath the substrate, so the printed circuit board would be down here. So the die is actually between the component substrate and the PWB, not on the top side. So that is a classical cavity down kind of a construction. This one's still wire bonded, okay, WB. So you can see that it's all wire bonded, but the wire bonds are all on the undersurface. So the solder balls, which is, of course, has to be a partial grid over here because the die is in the middle. So it's a partial grid array of solder balls with the component, wire bonded component sitting in between. Okay, so that's designed from one of Amcor's packages, the so-called Super BGA. Okay. Other renditions? Sorry.
What would be the motivation for this? Is it going thinner or?
It's part of it is just the profile, lower profile. I'm also wondering if they're trying to put some kind of a thermal management on the other side. I'm not sure. Not sure about that. Okay.
So when they're using this type of components, when they're using very tighter models, and they want to transfer the heat towards your chassis, what they'll mount it in the backside.
Okay.
So they have a cavity. In the PCB board, they'll have a
So
cavity.
there's a hole in there. Okay.
So total the component will come down,
Okay.
and it will be transferred to your chassis.
Okay.
It's all these are all used for the very low profile.
Yeah. Okay. And then here's just sort of a summary of a lot of the configurations we just saw. Classical. So this is flip chip on BGA. This is a combination. This is actually flip chipped and wire bonded. That's very unusual. What's going on there? Okay. Same thing with this one and with overmolding. This one actually is with glob top as opposed to molding. Molding is a pretty rigid material. Glob top is a much more compliant, almost like a silicone kind of a consistency material. Okay. And then cavity down has that thermal management on the backside. You now have that. So because your die is on the underside, you have the backside available to put heat sinks. So these are basically fins of a heat sink for air cooling purposes. Okay. All right. So these tables are just for comparison purposes. So you can see, for example, the interconnection for a CBGA. These are just flip chip bumps, but for most PBGAs, they are face-up wire bonded. Okay. You can have flip chip PBGA also, but unless it's specified, usually it's understood that these are wire bonded face-up, but they can be PBGAs with face-down flip chips. You can see underfills. So underfill in a CBGA, it's optional because the CTE mismatch is not huge, so you may or may not have underfills. Over here doesn't apply because this is face up, die facing up, so there's no question of underfill here. But in the plastic BGA with flip chip, you would definitely want to put an underfill here because you've got silicon on organic laminate, so you must have an underfill here. So that's what it says over here, it's required. Okay. Then, so you can keep going through the comparison. CTE mismatch between chip and carrier. So the CTE mismatch between the chip and the carrier, over here between here, and over here between here and here. So you can see since here both are ceramic, the carrier is ceramic, chip is ceramic, that's a very small CTE mismatch. Here you have a very large CTE mismatch, that's over here, okay, but it's attached with a die attach over here, okay, and and I'm sorry, and here down here is the CTE mismatch between the module and the PCB. Let's cover both of those, module and PCB. So over here, between chip and carrier, it's small, but between module and PWB, it's very large, because typically that's ceramic and this is organic, so there's a large CTE mismatch here, so that's what it says over here, pretty large CTE mismatch over here. So, oops, sorry. Then let's look at this configuration, which is the middle one. So there's a large CTE mismatch over here between die and substrate. That's this one. And but between the substrate and the PWB, it's not very large. There's some, but it's not very huge. Especially under the die shadow, there'll be quite a bit of mismatch. But once you're outside, the mismatch will be less. But it will, of course, still increase with DNP. Okay. And then for this one, again, there'll be fairly large CTE mismatch when you talk about between the carrier and the PWB that's down here. There'll be a reasonably large CTE mismatch under the footprint of the die, but again, once you're outside the die shadow, it's not going to be that high, and you can actually play around with it a little bit. Okay, stress level in the chip. So this is chip soldered onto ceramic. Not much CTE mismatch, so the die is not going to see a lot of stress. So chip stress is low. Here you've got CTE mismatch between the die and the organic substrate, and that mismatch is being partially accommodated in the die attach. So depending on how compliant the die attach is, you may have a reasonable amount of, so if you put a very stiff die attach, you'd have a large amount of stress in the chip. If you have a fairly compliant die attach, then the stress in the chip wouldn't be very high. Over here, because there's underfill and the solder joints, the stresses that are transmitted to the die because of CTE mismatch between these two is usually pretty high. So fairly high die stresses in this configuration. Okay, then second level. Okay, second level interconnection is down here, talking about these again. So for CBGAs, typically we saw those high lead solder ball and then eutectic solder fillets. So you can see that over here. These. So high lead solder ball and eutectic fillets. Okay, so that's what this one says. Oops. That's what this one says. Okay, and then in over here in the overmolded face-up PBGAs, it's typically all eutectic solder ball or eutectic sac or eutectic tin lead, meaning lead-free or tin lead, but just low temperature solder joints, nothing very fancy. And then same thing over here, typically it's low temperature solder joints here and higher temperature solder joints up here. Okay. Okay, reliability. Well, this one is definitely lower because of at the second level. This one has pretty high stress levels at the second level, so package level reliability is lower for these. Okay, so unless you added underfill for the BGA portion, the level 2, you would have pretty low reliability. Whereas in these, because there's relatively low CTE mismatch between the organic substrates and the PWB, organic PWB, the reliability is typically higher than what you would have over here. Okay. Of course, again, as I said, you could increase the reliability for any one of these by putting underfill over there. Okay. All right. Let's move on. Moisture sensitivity. Let's talk about that. Well, cost and moisture sensitivity. Cost, of course, ceramic modules are pretty expensive. The plastic versions are not that expensive. Okay. Moisture sensitivity. Anything with plastic molding is going to be pretty moisture sensitive. That means you're going to be worried about moisture ingressing into the package and residing in the package. It'll cause corrosion. And there's a second problem. So if these packages, think about it, if these packages are stored for a long time and they're under poor storage condition, that means not kept with moisture protection, they're going to absorb moisture over time. Then when you do the second level reflow, there's going to be a huge temperature spike. What's going to happen to all the moisture inside when you heat it up suddenly to 250 degrees C for soldering? You have an explosive evaporation, right? Sudden evaporation, so that's explosive. And it sometimes damages wire bonds, cracks, damages die attaches, cracks dies, and sometimes cracks the package itself in order to create an opening for the moisture to escape. What do we call that? There's a name for that phenomenon. Any of the students know that? You guys probably know it. Popcorning? No? Haven't heard the word. It's called popcorning in industry because basically it pops and it delaminates and the package cracks and delaminates with a popping sound. And I mean, we've seen this many times in the lab itself where we've done controlled tests just to study popcorning. So we have allowed moisture to ingress and then raise the temperature, spiked the temperature to 250 degrees C, and you get explosive failure in the package. It literally pops open, cracks and pops open the moisture to escape. So if you just Google popcorning and plastic microcircuits, you'll get a lot of information about it. Okay. So moisture sensitivity, that's why they're saying these are moisture sensitive. They can actually experience a lot of problems because of moisture. Okay. Okay. So here's an example of tab bonded BGAs. Okay. So in this case, these are the bumps on the chip. These are the inner leads of the tab film that have been bonded over here and then bonded to another pad over here. And then you've got the outer end has the solder joints that go to the solder paste on the board. So this could typically be these are high temperature solder balls, 1090 solder balls, and then put together with soldered down with tin lead eutectic solder paste. So low temperature solder paste, high temperature solder ball, tab that's been bonded to the chip, used to interconnect to the chip. So that's typically a TBGA. Okay. Okay, chip scale packaging. What is different about chip scale packaging compared to what we've been seeing so far? Well, look at the approximate. None of this is drawn to scale, but look at the approximate dimensions. The dimensions of the package are quite large compared to the size of the die, right? Again, dimension of the package are quite large compared to the size of the die, qualitatively speaking. None of these are to scale. But they've been drawn, although out of scale, they've been drawn approximately to reflect that fact that the overall package dimensions are significantly larger than the dimensions of the die. Okay? That's the kind of package we've been seeing so far. Here's the die, here's the package. Here's the die, the die is somewhere in here, okay? And there's the whole package, and so on. So chip scale package is an effort to further miniaturize these area array components so that they take up less space on the board. So to have your package meet the criterion of chip scale packaging, the package size should be no more than about 120% of your die size. Okay. So the overall substrate should be about 120% larger than your die, okay? And those packages tend to get very, very small. There are some chip scale packages that are just the size of the die. So meaning if that's the size of the package, that's also the size of the die. There's no outer perimeter beyond the die shadow or die footprint. So those are chip scale packages. And again, the central goal is miniaturization. So you can see it's 120% of the size of the die, 20% larger than the die. There's still area array. Everything else holds good. But the only difference is that the substrate is much smaller than we've been seeing so far, and they're about the size of the die. Okay? So you can see many different configurations here, different companies with their packages, Xilinx, Flip chip Technologies, Mitsubishi. And dies don't always have to be square. Sometimes they're rectangular dies. That's a rectangular die, that's a rectangular die. And the substrate is also about the same shape as the die. Okay. And of course, in some cases, there may be multiple dies on the other side. But these particular pictures I'm showing all have single dies. But there may be cases where it's rectangular because there are multiple dies side by side on the other side. Okay, typically a CSP will have, there are multiple kinds of CSPs. CSPs may have a lead frame or an interposer. So basically, the die has to be connected and redistributed to the pads on the bottom side of the substrate, of this substrate. And so therefore, that substrate may be some kind of a lead frame based or non-lead frame based or interposer based. So let's look at some examples of that. So that's what we're calling an interposer. There may or may not be an interposer. We're going to see several configurations. Okay, the interconnects are typically BGA solder balls, fairly small, and they may have encapsulants. So if the die is flip chipped onto the other side, then you'll have encapsulants on the other side. And even between the CSP and the PWB, you may have encapsulants because now that you have a very tiny substrate, about the size of the die, there's going to be a fair amount of CTE mismatch, okay? And sometimes they use underfill at the second level also. Okay, so let's see some architectures. I mentioned different types of CSPs. Some have lead frames, some don't, and we'll see examples of all of these. Some have interposers, and those interposers can either be rigid. By rigid, we mean reinforced, just like a printed circuit board. So the components that were being passed around, those are all rigid substrates. They are printed wiring board kind of material, organic laminates with glass fabric reinforcement. So those are what's typically called rigid interposers. Flexible interposers don't have any glass reinforcement. So these are, and also the materials have very low modulus, almost silicone-like, and the reason is to act as a stress relief between the die and the substrate to take away some of the CTE mismatch. Okay, so Tessera probably has one of the more well-known ones of the flexible interposer. And wafer-level type CSP, wafer-level CSP is basically the whole packaging, the CSP packaging is done while on the wafer before it's diced, okay? So chipscale makes quite a few of those. Actually, a lot of companies now make wafer-level CSP.
Is it meant like instead of a die attached to the substrate, the substrate
It's attached to the die, it's almost that, yes, exactly. That's a good way of putting it, yeah. Okay. So a lot of text, unfortunately, on this on this slide, but those are the four. Okay, the lead frame based, the rigid substrate based, rigid interposer or substrate, flexible interposer or substrate, and wafer level CSP. Okay. So there's a lead frame design over here, but it's not the kind of lead frame we've been seeing so far. It's slightly modified because these are very, very tiny. Okay, and these. We'll see some examples of this. And oftentimes these lead frame based ones are wire bonded. Okay, they're not flip chipped, they're wire bonded. Okay, so in the rigid, it's going to be either a reinforced laminate, okay, organic reinforced laminate, or a ceramic substrate. So either of those is a rigid substrate. So the chip is interconnected to that substrate, and then the substrate has solder balls to go on to the PWB. So this is not too different from all the BGAs we've been seeing so far, like these, okay, like these. The only difference is the size of the substrate is about the same as the size of the die. That's all. Okay. Okay. And then the flexible interposer, there's a flexible layer of material. And it's typically not a classical laminate because it doesn't have the glass fabric reinforcement. So it's a special kind of material. And those materials are usually, it's a thin layer, okay? And it's relatively easy to do high volume manufacture because they usually do roll to roll for these to manufacture the interposers. Wire bonding and tab is typically what's used to connect the chip to that interposer. And actually flip chip is also being used. I'm not sure when we made the slide, but flip chip there are a few examples of flip chip also now. Okay. So yeah, and these are all solder bumps, there's no leads on these are all solder bumped. Okay. And then wafer level, so the chip packaging takes place at the wafer level rather than at the individual chip level, and as you said, sort of approximately. So you're doing the packaging while it's on the wafer, so you're putting all these interposers and solder balls onto the die rather than the die onto all of that. Okay. So here are some examples of CSPs. This is a lead frame based CSP. It's a no lead. There are no leads. Okay. So be careful. There's a lead frame, but no leads coming out of the package. Okay. So this would be like a QFN, quad flat no lead package with a big metal mass in the middle. That's for thermal management reason. So all of this gets soldered onto the package. The middle one is to transfer heat below the die, and the outer ones are the electrical iodes. Okay, so that's the back side of that component. This is just a schematic of the lead frame. So this is the center exposed paddle is this one. That's that big copper slug here. That's to remove the heat. So there'll be a solder under that, and that'll transfer the heat to the PWB. And then these copper pads for the I/O are out here, okay? So those are connected to the silicon chip, and that carries the electrical circuits in and out. So one of the names for this that's been floating around in the literature, so QFN is one of them. Sometimes they also call them MLFs, micro because it's chip scale package, lead frame because it has a lead frame, so MLF packages. Okay. All right, let's move on. Okay. So this is here the terminology is micro SMT, okay, surface mount technology, micro SMT. So this is also a lead frame based. And here this whole package, so there's a lead frame mounted onto the IC, and then an encapsulant, and then a cap put on top of that. These are all put on by thin film technology, okay? So you can put the whole thing on top of the IC, and you can do this, in fact, at the wafer level, okay? So chipscale makes these kinds of packaging at the wafer level, okay? All right, so here's a rigid substrate based. So now we talk about the rigid substrate and the flexible substrate based CSPs. So again, you can see there's nothing dramatically new. You have a rigid substrate, you have a die, you have a die attach, you have a mold compound, you have a wire bond, and you have a redistribution to the back face where you have the solder bumps. Nothing new other than the fact that now the substrate is not a lot bigger than the die. That's the only difference, okay? So the package size is no more than 20% the size of the die, so that's why it's a CSP as opposed to a regular BGA, ball grid array, okay? Okay. And you can see they come in various pitches, 0.5, all the way up to 0.8 millimeters. Okay. Okay. Here's another set of designs from Amcorp chipscale. This is their flexible BGA. Again, as far as the schematics go, there's nothing dramatically new here. They have two versions: a face-up, wire bonded, very classical, and this one actually looks bigger than CSPs should. But in reality, it is a CSP. This one is probably not drawn to scale. The substrate should have looked a little smaller here. But basically what this says is Amcorp has two CSP designs, face down one, a flip chip face down one, and a wire bonded face up one, okay? Okay. Here's Xilinx's version. So these are all rigid, by the way. This is a rigid interposer. This is a rigid interposer. The word interposer and substrate are being used interchangeably. So this is also a rigid interposer, a rigid substrate. Same thing with the Xilinx. It's a rigid interposer or substrate. Nothing dramatically new otherwise, okay? Here is Motorola's rigid interposer. So this is a multi-layer rigid interposer, chip scale. You can see the substrate is very small compared to the die, okay? That's just taken, that drawing is taken out of a patent. That's why it looks that way. Okay. All right. Patent number 651 is the 089 patent. Oh, that's just all parts are numbered in a patent. You have to number every part and name what that part is in the patent. So patents are legal documents, so they are very touchy about having everything labeled, everything named, just so if you're accusing someone else of infringing on your patent, you have to go item by item and show that they're infringing on all of them. Okay, so it's a very legalistic aspect of it. Okay, all right. Okay, now we move on from rigid substrates to flexible substrates, flexible interposers, and as I said, probably the most widely known of these flexible interposer substrates is Tessera's Micro BGA. And here you can see that's the silicon die, okay? And this is an elastomeric material. Elastomer is very low compliance, very low stiffness, almost like silicone rubber kind of stiffness, okay? So elastomers are very compliant materials. There's no rigid material in here at all. The only rigid material is the silicon. So what gives the package its handling stiffness is just the silicon. Everything else is just a very compliant material on it. Okay, there's no rigid substrate to it. which means the handling and all is, you have to do very carefully, because any handling stresses are directly going into the die. There's nothing else protecting it. Okay? But they're very, very tiny, so it's hard to actually bend it during handling, because it's a very tiny package. Okay. So, and these are just the electrical connection from the die face to their bonding leads that they use, flexible, slender copper leads that they use to go from the bond pad on the die to the bond pad of the solder joints. So everything, the idea is that everything here is compliant. So mechanically, this solder joint is somewhat decoupled from the chip. Okay, everything in between the solder joint and the chip is very, very compliant and can deform. So the solder joint is not, although this is now going to be soldered down on the PWB, the solder joint is not going to move with the die. It's going to be just fixed on the PWB, and the die is going to shrink and expand, and all of those mismatches will be taken up in the elastomer. Nothing else is going to deform. Okay? So the idea is to extend solder joint life. Okay? So here are some more concepts for compliant interposer designs. So again, this is now this picture turned over. The solder joint is on the top, the die is on the bottom, so just flipped that image upside down. So the die is on the bottom, solder joints are on the top. This is a multi-layer compliant substrate, and here is the decoupling layer, highly compliant decoupling layer. And the whole idea is that the electrical connections through that mechanical decoupling layer, the electrical connection should also be compliant. Otherwise, you cannot preserve that compliance through the layer, right? So in this case, they're using these serpentine slender copper leads. In the previous case, Tessera, they'd used a flat but very slender, flexible copper lead, copper tape almost, okay? Actually, it's not even copper. Yeah, that's the bonding lead, correct. That's the bonding lead, sorry. Okay. And then, yeah, so that's how we get the electrical signal from the pad on the die to the redistribution layer here. And then the redistribution layer takes the signals to the various solder joints through micro vias. Okay. So these are various concepts. So again, there are multiple manufacturers who use some version or other of these kinds of flexible interposer CSPs, chip scale packages. Okay. This is just another picture of Tessera's. I'm not going to spend time on it. This, in fact, you could probably look at this one and see what it actually looks like. So your whole substrate is actually just the die. The die itself is, I mean, the rigid part of your component is the die, and everything else is just a thin compliant layer, thin film technology, and then the solder balls on top of it. That's it. That's the entire package. So in this case, it's not even 20% larger than the die. It is just the size of the die. Okay. Okay. All right, and then these are some more versions. We'll skip over these. There's several. You can look through those later on. That was NEC's package. This was Nitodenko's package. They all have some version of, the common features are a compliant layer, thin film layer, and compliant interconnects. That's all. Those are the two requirements. Different people have different ways of achieving that. Okay, and the reason they have to use different ways is otherwise you have patent infringement issues and stuff like that. Okay, this is a wafer level CSP. Okay, so this is done. Think of it as turned around. So that would be, this would be part of the wafer. The silicon chip is on the wafer, and you build all of these layers up on the wafer by various thin film technologies and various deposition technologies. You build up all of this interconnection structure on top of the silicon chip, and then you dice the silicon chip, and that's your package. Once again, the package size here is the same size as the die itself. It's not 20% larger. Okay? So this particular one is just a schematic. It's not a real picture, obviously. That's the Fujitsu Super CSP. This is just a schematic of what the technology there looks like. Okay. So this is, again, a chip scales version of a wafer level CSP. So again, there's some detail shown over here. to show what their interconnection looks like. So it's not quite a solder ball like it is over here. It's really more of a solder, it's more of a metallization bump, and it's a kind of a complex bump. The main profile is made by just a polymer. It's a post, okay, a bump or a post made with epoxy. And then you have deposited on that various combinations of insulation layers and metallization layers to get signals in, make sure there's no crosstalk, so there's some insulation layers, and then metallization layers to the appropriate bond pads on the chip, to get the electrical circuitry there. And then on top of that, you have a solderable metal. Now you can solder that, these posts onto a printed circuit board with solder paste, because you put down some solderable metal over there. Okay? So these don't come with solder balls or bumps. They come with these posts. So these posts get directly soldered onto the component. Notice, though, that there is no compliant layer over here. Unlike the flexible interposer technology, this is almost this is as close as you can get to putting silicon directly onto the PWB, other than flip chip technology. Flip chip technology is the same thing. So this is almost the same level of solder joint stresses as flip chip technology does. So this often needs underfilling because of that. Okay. Okay. So this is flip chip, a company called Flip Chip Technologies. They also make these ultra CSPs, which are basically nothing but flip chip joints with a little bit of packaging on top, okay, a redistribution layer rather on top. So instead of, these pads are not directly on the die, they're on a redistribution layer. So the I/O pattern on the I/O pads on the die may not be quite this kind of a pattern, maybe a little different, but they've been redistributed into this pattern on this redistribution layer. But the redistribution layer is extremely thin, so it's almost as good as just a flip chip. The difference is this actually has a solder ball. This one did not have a solder ball. This one actually has a solder ball. Okay? So no other interposer, okay? Just the solder ball and the IC. Okay. 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 So we already saw a couple of designs that are almost interposer-less. Okay. And then let's move on to stacked chip designs, where now all of these were single chip. All of these were single chip. Let's move on now to multiple dies stacked together, 3D or 2.5D designs. So let's skip this. This is, again, interposer-less. So this is the die. You directly build on the solder bumps with some metallization, redistribution layers on that die itself. And then this is just resin material over there. That's really not an interposer. It's just a cover. And directly build the bumps onto the die. So that's interposer-less. Okay. All right. So now let's talk about these multi-chip modules and stacked dies. So this would be, just again terminology, this would be what you would classically call a 2D multi-chip module. SIP stands for System in Package. That's because you've got a whole system, could be active dies, passive components, combination of all of those in a single substrate. So it's a system in package. And these are flip chipped. The dies are flip chipped onto a substrate. Then the substrate is ball grid arrayed down to a circuit board. So this would be a classical two-dimensional because they're all in one plane, okay? Two-dimensional multi-chip module. Sorry, backwards. As opposed to that, you can have the so-called 2.5D, where the only difference is you have another interposer in between that's used to redistribute these interconnects onto a different pattern. So instead of directly having those patterns go on the substrate, the die patterns are redistributed into another common pattern that goes in the substrate. And then as before, the substrate goes in the PWB with ball grid arrays. So the presence of this interposer redistribution layer makes it a 2.5D as opposed to a 2D. Okay? So the TSV stands for through silicon vias. So this interposer is made out of silicon, and these vertical lines are vias going through the thickness of that silicon layer. So these are through silicon vias. Okay, and then these solder joints are typically micro bumps. They're not even balls. They're very tiny. These are micro bumps. Okay. The reason you can make them micro bump is because there's silicon on silicon, so there's very little CTE mismatch, almost no stresses. So you can make these solder joints very, very tiny. Okay, now let's get to much more complex pictures, and there are 4 different renditions here of 3D packages. 1, 2, 3, and 4. Let's walk through them. So this is a classical 3D die stack of 2 different dies that are wire bonded. Okay, so you can see these have been wire bonded either to. So sometimes you'll get wire bonds going die to die. Sometimes you get wire bonds going die to substrate. So various combinations. So these are 2 dies, die 1 and die 2, that are stacked on top of each other and talking to each other through wire bonds. And then the lower one is flip chipped onto the substrate, and then ball grid array below that. So there's no interposer redistribution layer over there. So that's a fully 3D configuration. Okay. Here's another one which has more than 2, many dies, all talking to each other through metal wires that are running down the outside. So if you have a die, they basically pattern metal wires running down the side, talk to the next die, metal wires running down the side, talk to the next die, and so on. So there are over here on the sides, actually they've shown it on the sides, those double lines on the sides are schematics of metal wires that are, so instead of having wire bonds come out, think of wire bonds that go right down along the sides of it. It's almost like that. Okay. Okay. Then here's another case where you have silicon dies talking to each other, and they are not wire bonded, but through silicon viaed to each other. So this is not an interposer. Unlike this is through silicon vias through an interposer, these are vias through silicon dies themselves. Okay. So these are dies talking to each other through TSVs, and then ultimately using a substrate component substrate. So that too is a fully 3D construction where dies are stacked on top of each other and directly talking to each other without having to go through an interposer to talk to each other. Okay. Okay, and then this is just a build-up of all of these different technologies. You have multiple dies, 2 dies over here. So this portion of it is a 2.5D. This bank of dies talking to this bank of dies is through this interposer, so that's 2.5D. But then within each bank, you have 3D banks over there. Okay, so it's hybrid combination of 2.5 and 3D building up to make very complex packages. So this is where heterogeneous integration is going now. So some of these dies may be photonic. Some of these may be RF, some of these may be analog, some of these may be digital, very complex combinations of banks that are, some of these may be MEMS sensors, some of these may be biosensors. So, and of course I'm speaking somewhat qualitatively here. The real designs get pretty complex, and the real designs, there are only some limited examples yet, but the vision is that they'll get more and more complex as time goes on. So the way people are increasing the functionality of so all of this is one single component, okay? So the way people are increasing the functionality of components is by this kind of multi-level heterogeneous integration, rather than trying to put a lot more onto a single die itself. So use multiple dies rather than a single die. That's what heterogeneous integration is all about, okay? Okay, here are some pictures. Yeah, oh, sorry, yeah.
What is the actual difference between this 2.5D?
Okay. In a 2.5D, this die cannot talk to this die directly without going through the interposer in between. So the signals go to the interposer, and through the interposer redistribution, it can go into die 2. So they cannot talk to each other except through the interposer. It takes time. Here, they're talking directly to each other. There's no interposer to go through. The dies are talking directly to each other. Yeah. Well, 2 ways. In this one, 3 ways. In this one, through wire bonds. I haven't shown the wire bonds between the dies. There are also wire bonds between the dies. Here, the wire bonds are very specialized. They are metal wires running along the sides of the die, as I said, metal patterns running along the sides of the side of the dies. And in this case, through TSVs. Okay? But there is no other redistribution layer. It doesn't have to go down into a TSV through that and up into the other die. It's directly going into the other die.
Electrical
No, speed, big difference in speed. Yeah, yeah. It doesn't have to go through the interposer and out again. So yeah, for high frequency circuits, there's a big difference. Yeah. Yeah. Okay. And here are some actual examples of wire bonded 3D die stacks. Okay. So you can see here's a larger die, smaller die. The two dies are talking to each other directly through wire bonds. So that's a 3D stack, not a 2.5D. Then this die is talking to another die next to it, not stacked on top of it, but next to it, but directly talking to that die. And then there are some that are going into an interposer down below, and that interposer will go connect somewhere else. Here you can see all of these dies are connected to some interposer. Although they're stacked on top of each other, they're all going down to a single substrate over here. So various combinations, okay? And you can see over here, so here's an interposer. Both the dies are connected through wire bonds to that interposer, so they can only talk to each other through that interposer. Over here, it's let's see, 2 die and 2-layer laminate structure, 2 die on 2 same size die stacked. Oh, the only difference here is it's the same thing, wire bonded to an interposer. The difference is here, the 2 dies are the same size. Here they're different sizes, so it's easy to wire bond both because the lower one is sticking out. Here they're the same size, so they had to put another spacer in between so that they could get the wire bonds out of the lower die. And here they are not only going down into the interposer here, they're also talking to another one laterally. So 2 dies stacked over here and one more stacked over here, and they're talking to each other through the interposer. Okay. Oh, sorry. So that's more of similar kinds of pictures. Here is a crossed die approach, by the way. So this cross section really is of this component. So you've got wire bonds from this lower layer coming out over here, wire bonds from the upper layer coming out over there. So you can interconnect to both dies to the substrate. This is the example with a spacer. So there are actually spacers between these dies. That's why you can see the gap. Sorry. There are spacers between these dies. That's why you have the gap. That's for the wire bonds to come out of those lower layers, inner layers. And then this is a more classical, smaller die on top of a larger die, easy to wire bond. Okay. And again, you can see more and more examples of different kinds of die stacking, different sizes, with spacers, without spacers, crossed dies, all of them together over here. So it gets to be quite a mess of wire bonds at the end of the day, but it's doable, and people are actually doing them. Okay. Now die thinning, this is, I'm intentionally staring at that number a little bit. 50 microns is already very thin. That's a very thin die. But we were looking at internet yesterday, and they were talking about under 15 micron dies. Amazing. Okay. So these dies are, of course, pretty large. You couldn't make 15 micron dies that are this big. So these are probably 50 microns is pretty thin for this one. But people are apparently going, and I had heard of dies down to 20 microns thickness. He found some on the internet yesterday that were like 12 or 8 to 12 micron thickness. Very hard to even imagine. That's completely flexible, right? Okay. So die thinning is a big challenge. How do you handle such a thin die? Just as an analogy, I was just reminding him, your human hair is 70 microns. These dies are already thinner than human hair. 8 to 12 microns is 1/10 the thickness of human hair. That's how flexible it's going to be. How do you even handle something like that for dimensional registration and so on, right? Some pretty smart technology there. Okay. There's also these other stacking technologies where you're not just stacking within a package, you're stacking package on package. So that's also done to save space, to put in more electronics onto a smaller footprint. People also do package on package. That's already being done. So in this example, you have a 2-die package over here stacked on top of a single die package over here. Both are ball grid arrays. The upper one is a partial array ball grid array. Well, both of them are partial array ball grid arrays. and you can actually see photographs of what that looks like. Okay. All right. So, so these are more 2.5D and 3D. So this particular one appears to be a 3D die stack. It's going through microvias through each of the layers. So yep, that's a 3D hybrid memory cube from Micron Technologies. This one is 2.5D because Xilinx actually interconnects them through a redistribution layer, not directly to each other, but through a redistribution layer. There's a 65 nanometer interposer there that does the redistribution. Okay, and this is just an artist's rendition of what the future is going to look like or may look like if heterogeneous integration works out the way people would like it to work out. Someday you're going to have a package that looks like this. I put up a picture like this, the same picture I think yesterday. I'm just putting it back up to remind everyone. So you've got within this package, you've got batteries, power supplies, RFs, digital, optoelectronics, and then on top of that package, so all of that is in one package, and then on top of that package you have more packages, so you have package on package. So, well, you have a system in this package, system in package, and then packages on that package, so it becomes a system on package. This is, by the way, that's Rao Tumala's terminology. He calls that system on package. And basically, that's the vision of what the future is going to look like. That's what electronics will look like in the future. Okay. Sorry?
Is it a mobile?
We don't know. This particular one is just, they've taken all the different known technologies and just put them all into one picture. Well, what it's actually supposed, there's not a real part, so we don't know what this one is supposed to do. You can see it's got biosensors, it's got, what else? It's got RF. Well, RF could be for many reasons. It's got opto, it's got digital, it's got MEMS, it's got some wide band gap transistor there. I'm not sure why, that's an LED maybe, and so on. And 3D die stacks, so a lot of stuff going on here. Maybe. Yeah. All right. Okay, what time is it? It's about 4:30. There's tea outside today? Yeah, okay. And then actually it'll be almost 5, but then what I'd like to do is take a few minutes to just introduce what we'll talk about, not tomorrow. Tomorrow Professor Anandaroop is going to do thermal, and I'll be sitting in there where he's sitting, so it's my day off. I get to listen. And then day 4, I'll come back and talk about some advanced packaging concepts. In fact, I don't need to put up slides for that. I can briefly talk to you. Well.